Hello everyone, I hope you're doing well. So in today's video, we are going to go through the 2023 Northern Hemisphere VCE Chemistry exam, part 2 of the short answer questions. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this paper. Question 6. In some countries, most cars are powered by petrol engines, whereas most trucks are powered by diesel engines. Petrol is a mixture of saturated hydrocarbons, including octane and dodecane. Write the balanced thermochemical equation for the complete combustion of octane at standard laboratory conditions. Easy, let's do that. So I'm going to write it at the top because I think there isn't a lot of space here, so let's do that. So we have, what is it? Complete combustion for octane, so which is C18, so it's C8, sorry. H18, is that right? Yep, C8, H18, let's do it. So we know octane at, standard laboratory condition is at, liquid. It's a liquid, actually. And you can see that in your formula, stat data booklet. So at standard laboratory conditions, it is a liquid. And so when we react it with oxygen gas, it will form, of course, water, so H2O. And remember, at standard laboratory conditions, water is a liquid. So liquid state, and CO2, which is at its gaseous state. Now, let's check one thing. Now, we can see that there's 8 carbons on the left, so we're going to have to put 8 carbons here to make it the same. We can see that there's 18 hydrogen, so we have to put 9 here to make them the same. Now we have how many? We have 2 oxygens on the left, and we have 9 plus 16, which is 25. So we have 25. So to make them equal, we're going to put 25 on 2. Now, normally we don't like having fractions, so we're going to actually get rid of that fraction. I'm going to multiply everything by 2. So I'm going to write it at the bottom bar. So take this, I'm just going to multiply everything by 2. Bring this here, and let's do that. So, it's going to be 2 C8 H18 at liquid plus 25 oxygen gas gives us 18 H2O liquid and 16 CO2 gas. Beautiful. Everything is doubled, so in 18, 16. And that, what's our M flippage change? Remember, it is a thermochemical equation. We know it's going to be a negative because it is a combustion reaction. So we can see that we have 2 moles of octane. So we can actually use our data book here to go down to, okay, here's octane. Octane is right over here. You can see that it's at liquid state in standard laboratory conditions. We know basically every mole, it produces 5,460, but we have 2 moles in this equation. You can see that there's 2 moles of it. So we just basically have to double it. So what is 5,460 times 2? Basically, it's going to be 10920 kilojoules per mole. Done. Easy. That is a nice, easy question. Very, very easy. Let's do the next part. 1 mole of octane is completely combusted, and the carbon dioxide produced is captured in a 100-liter gas cylinder. The pressure of the cylinder is this. Calculate the temperature of CO2 in the cylinder. Now, they're not telling us in degrees or Kelvin, so I'm just going to make sure it's in degrees. Very, very easy question. So, I know that the number, so we have how much? The mole of, we have 1 mole of the octane is 1. And we know to calculate the mole, because we want the CO2, so the mole of CO2 is how much? It's 1 times, by using stoichiometry, so it's going to be 16 divided by 2. So 16 divided by 2 to get 8 moles. So what are we saying? For every mole of octane that is combusted, we produce 1 mole of CO2. And now we can use our gas universal formula, so PVNRT, to calculate the temperature, where temperature is basically PVNR. That looks good. So, P is the pressure, which is 255. Volume is 100. The mole is 8. And the, R value is 8.31. Remember, it is given in your data book. It is a constant. And so that's going to give you what? So let's write that down. 25 times 100. 8 times 8.31. That gives me 383. basically like 6, and that's in Kelvin. Remember, that's in Kelvin. Now I'm gonna make sure it's in like I think you should leave your answer in Kelvin, because it's not telling you, but I normally will leave it in degrees Celsius. So just make sure you minus 273, and so basically your temperature in degrees Celsius is how many two decimal? So looks like 3, the lowest significant figures. So 111. Yep. So 111 and degrees Celsius. Done. Very nice. A tank contains 11.75 liters of water at standard laboratory conditions. 34 grams of, dodecaine is completely combusted, and all of that energy is used to heat the water in the tank. That's good, so there's no energy loss. After being heated, the final temperature of the water is this. Use the information to calculate the heat combustion of dodecaine in kilojoules per gram. Very, very easy. So we want it in terms of kilojoules per gram. So kilojoules divided by grams, basically. So we need to calculate the energy that basically the dodecaine releases every gram. Now we basically how much are we burning? We're burning 34 grams. So we already got the mass. We just need to see how much energy is that going to release in kilojoules. So let's do that. Now we're going to use MC delta T because it was given to the water. So energy is MC delta T. We need the mass. We need of course we have 11.75 liters. We want to turn it into grams. How do we do that? Easy. Make sure it's in milliliters first. So 11.75 times it by 1,000, you'll actually get it in milliliters. And so that gives me 11,750 milliliters. Why do I convert it to milliliters? It's because you're going to use this formula where basically, if I go here, where is it? Basically, for every milliliter, it's basically equivalent to 0.997 grams. So let's do that. So multiply that 0.997 by that 11,750 milliliters. And that's going to convert it into grams. That's our goal. Let's do that. Times it by 0.997. And that gives me 11714.75 grams now. Easy. Now we can use our formula. So E is equal to the mass, which is 11714.75, times your specific heat capacity of water, which is 4.18. It is in your data sheet. And the change in temperature. Now, we know that the final temperature is 57.2. And of course, the water started at CLC, meaning it started at 25 degrees Celsius initially. So the change in temperature is 57.2 minus 25. So this is going to give me the answer, 4.18 times 57.2 minus 25. And so that gives me overall it's a very big number. So I'm just going to basically divide it by 1,000 to get it into kilojoules. So it's the same. In terms of energy, it is 1576.758 kilojoules. So we've got the kilojoules. Now we just divide it by the mass. So if we divide it by the mass, how much do we burn? So 34 grams. We get basically our enthalpy change. So your combustion, your enthalpy to be what? Cut the heat combustion, 46. So how many specific heat capacity? So to 3 significant figures. So 46.4 in kilojoules per gram. Done. Very beautiful and easy question. Let's do the next question. Okay, modern trucks can run on a mixture of petrodiesel and biodiesel, or in some cases, pure biodiesel. Compare the renewability of petrodiesel and biodiesel. In your answer, refer to the sourcing of petrodiesel and biodiesel. What an easy question. It's only 2 marks. So I think the first mark comes basically by saying which one's renewable, and then stating why is it renewable because of the sourcing, relating it to its sourcing. Now, of course, easy. Petrodiesel is non-renewable. whereas biodiesel is renewable. Why is that? Because petrodiesel is taken from fossil fuels, especially petroleum, or in other words, petroleum is called crude oil. And what it goes through a process called fractional distillation, where it basically separates. It separates to different fuels like octane, diesel, petrol, all these. So, but remember, it comes from fossil fuels, which takes very, very long to renew. So hence, it is non-renewable. Whereas biodiesel, in the other words, is basically sourced from organic matter, such as canola oil, where canola oil, seed oils, all these, and they go through like the esterification. It's like an esterification reaction of fats and oils. So that's what it goes through. Biodiesel is that it's sourced from esterifications of fats and oils in those oils, like seed oils, canola oils, and there. So, but biodiesel is renewable because we are taking it from basic plants and organic waste or matter. So that's it. So petrodiesel is non-renewable, biodiesel is renewable. So we only need to say, because it's only 2 marks, this is what we're going to say. So we're going to just have to say which one's renewable first. So petrodiesel is non-renewable, whereas biodiesel is renewable. Beautiful. So we know that petrodiesel is sourced from fractional distillation, of petroleum. Petroleum or crude oil basically mean the same thing. Petroleum. I don't even know if I spelled that right. Which is a fossil fuel. Biodiesel is sourced from the esterification of fats and oils of organic matter. Beautiful. That is it. Very nice and to the point. E. What is meant by hygroscopic properties of fuel? The hygroscopic, what does that mean? It means the ability to absorb water. Now, basically, yeah, so some fuels, what they do is, like, for example, biodiesel is very hygroscopic. Why is that? It's because it has an ester group, which basically it creates this polar part of it. And so remember, if there is a polar part of it, it likes to basically bond with water. Remember, water is polar, so it likes to create bonds, and so it attracts water and hence absorbs it. Basically, if it absorbs water, it's bad because it decreases the efficiency of the fuel. And why is that? Because we have to put more energy to to get rid of that water. What's that word? It's just out of my to vaporize that water. You need energy to first vaporize that water. So yeah, it really does destroy the efficiency. So hygroscopic properties of fuel is its ability to absorb water. That's it. Very 1 mark. So ability to absorb water. Beautiful. Explain the difference in the hygroscopic properties of biodiesel and petrodiesel. This is what we just talked about. Remember, biodiesel is more hygroscopic than petrodiesel because of that ester group that makes it slightly polar and hence attracts water. Petrodiesel is just totally non-polar. It's just a straight chain of non-polar and only basically has dispersion forces, and so yeah, it does not attract anything. So that's why it's very efficient. Petrodiesel is much more efficient than biodiesel. So that's what we're basically going to write. So let's use this here. So biodiesel is more hygroscopic than petrodiesel because of the ester group that makes it slightly polar, which attracts water. petrodiesel, is non-polar and only forms dispersion forces. So what am I talking about? Biodiesel is more hydrophobic than petrol because of the ester group that makes it slightly polar, which attracts water. Petrodiesel is non-polar and only forms dispersion forces. It does not attract water. It's saying that, so yeah, it does not attract water. It does not attract water. Beautiful. Nice question. Question 7. Let's have a look at this question. Copper metal is used to conduct electricity through a printed circuit board, or PCB. One use of the PCB is in computers. Electrolysis can be used to deposit copper on the PCBs. State the structural feature that is present in an electrolytic cell but absent in galvanic cell. Easy. One of the most common thing is the salt bridge. The salt bridge is not in electrolytic cells. Whereas in galvanic cells, you need it. And why is that? It's because in an electrolytic cell, you actually don't require two containers. Because remember, in galvanic cell, what you have is those two sources, those two reacts are very they basically react spontaneously, which is a bad which we don't want them to react spontaneously like that. In electrolytic cell, because they are non-spontaneous, we can actually put them in the same vessel. And so, yeah, we don't actually need a salt bridge. That is the one of the most kind of common things that electrolytic cell, it does not have. So that is present. Wait, state the structural features that is present. Oh, I'm doing the opposite. Wait. State the structural features that is present in electrolytic cells, but absent in galvanic cells. Not electrolytic. Didn't answer the question because I thought it was the other way. But the battery, your source of power, that is one of the main things that the electrolytic cell has, whereas a galvanic cell does not require, because it basically transforms chemical energy to electrical energy. So a battery or battery source, so just battery. Very nice and easy. State one advantage of using copper over platinum as an anode in the electrolysis cell used in deposit of copper on the PCBs. Easy. We know that platinum is very, very expensive. I'm being honest with you. Platinum it's one of the most expensive actual things to produce. And that's because of its non-reactive. It's not very reactive. And also, it's state the advantage of using copper over platinum as the anode in electrolysis used to deposit. And actually act as a catalyst. Most of the time when we use it, it's a very good catalyst that basically increases the rate of reaction. So overall, platinum is not basically the one of the best things to use, especially for this, is because it's very expensive. I think that's one of the best things to talk about. And state an advantage of using copper. Copper is very inexpensive and it's very readily available and it's very cheap. So state an advantage of using copper over platinum as anode in electrolysis use deposit. Copper is cheaper than platinum, so we can say that. Copper is cheaper than platinum and is easily and is readily, let's say readily, much more nicer, readily available. Beautiful. So copper is cheaper than platinum and is readily available. That is good. See, in a particular electrolysis cell, a number of PCBs have copper deposited on them. The electrolyte used in the cell is this. The electrolysis cell is operating at 4 amps. Assuming the 100% cell's efficiency, for how many seconds does the cell need to operate in order to deposit 5.0 grams of copper on the PCBs? Easy, 4 marks. So, first, the thing is, it's actually very easy because it's 100% cell efficient. So, there's no loss in terms of power. So what we need to first do is calculate the number of moles of electrons so we can get, to the other process. So what are we going to do is calculate the first mole of copper. So moles of copper is the mass, so 5.08, divided by your molar mass of copper, which I have no idea what it is. So let's check that out. So molar mass of copper. Where are you, copper? 63, wait, is that it? Yep, 63.5. 63.5, is that right? CU? Yep, 63.5. Done. So, we have that, so let's write that down. What does that give me? 5.08 divided by 63.5. And so basically that gives me 0.08 mole of copper. Now we need to get the moles of electrons. And to do that, we need to write the reaction of copper. And luckily, we have it in our electrochemical series. So let's write that down. Where is copper? Where is it? Yeah, there it is. Copper is right there. Let's write that down here. So copper 2 plus. I'm not going to write aqueous and stuff just because I just want to get it quickly done. Goes to copper solid. All right. That's all we need right now. Okay. So if I want to get the number of moles of electrons, what is it? It's basically taking it's going to be the moles of copper. What's the ratio? It's 2 to 1. So times that by 2, we get 0.16 mole. And so now I can actually get the charge. So your charge is what is it? Oh, what am I doing? So you don't want this too quickly. So number of moles of electron is your Q over F. So it's your number of moles of electrons times your Faraday's constant. So basically 0.16 times 96500, which is in your formula sheet. It's the constant, Faraday's constant, which basically results me with 15440 charge. And so now I have this. I know that Q is equal to I times current, so I can calculate now the time. So time is your Q, which is what we have right now. So 15440 divided by the current, which we know is 4 amps. So that gives me to, how many significant figures do we want it? The lowest is 2, so 3.9 times 10 to the power of, so 1, 2, 3. 3 seconds. Done. Beautiful. D. Another electrolysis cell is set up at standard conditions with 2 platinum electrodes and 1 mole of sodium hydroxide as the electrolyte. Write the equations for the 2 half equations that occur. Easy. So we're using, the platinum, so we're using platinum so they don't react, and we're using 1 mole of sodium hydroxide, which is probably in its aqueous state. So yeah, NaOH. So Na, we're going to have Na plus ions, OH minus ions, and of course it's in an aqueous state, so it has to have some water. So having all these, let's highlight them all in our electrochemical series. Now, where is Na plus? Na plus is right there. O water, so water is here normally and also here. And we also want OH ions. Now, where are they? Okay, OH ions. Yep, we can have that one by itself. What else? We cannot have that one. Be careful because you need hydrogen gas to go through that reaction. So not that one. So only these. So beautiful. So which one is going to be our reduction reaction? Which one's going to be the strongest oxidizing agent? And remember to do that, it's on the left and it's the highest one, which is this one here. So this one is going to basically get reduced. So let's write that first one. So write the equation for the 2 half equations. So it's going to basically be this one here. So the first one, 2H2O liquid plus 2 electrons gives us H2 gas plus 2 OH minus aqueous. That is the first part. And your other part is, you remember to find the strongest one that's going to be oxidized or the strongest reducing agent is going to be the one at the bottom and it's going to be on the right. So this one here. So it's going to be 4OH. So that one. 4 OH minus aqueous gives us oxygen gas, 2H2O liquid, and plus 4 electrons. And that is it. Jackpot. These are going to be your reactions. These are the ones. Oops. All right. So that is good. Now let's move on to the next part. Next question. Question A. Yes. Chemical P contains only carbon, hydrogens, and oxygens. There is 1 oxygen atom in the chemical P. Easy. So basically that limits us. We can only have an alcohol, it means. We can have an alcohol or a ketone that has 1 oxygen or an actual aldehyde. So these are the possibilities that we can have. The infrared spectrum is shown. Identify the type of bonds in chemical P around that 3,350. So this peak here in the IR spectrum. So what is the bond? Easy. To do that, let's use our data sheet. So I do have an extra part in my data sheet that I put to help out a lot of students how to simplify everything. Here it is. It's one of the best things that I've actually put. Here it is. It's like this extra. It is not in your data sheet, but I've put it as an extra in my one to show students how easy it is to do these questions. So 3,350, where is that? It's between this here, this part here. Now, this tells us what the possibilities are. So this peak could be an N to H, one, an O to H, or a C to H. Of course, it's not an N to H because remember, there is one oxygen and there's no nitrogen. So rubbish. Take that out. And the CH, let's check if it's a CH. Go up here from my other part here. C to H. To have a C to H, it needs to be between this, which we don't have. Remember, our one is 3,350, so rubbish. So it cannot be the CH. So it has to be your O to H. Now, can we double check that? Absolutely, we can. So is it an alcohol? Yeah, it does actually closely fit related with this here. And it is a strong bond. Strong and broad. Yeah. So it could be an alcohol. Could it be a carboxylic acid OH? Nope. Very, very small. So yeah, it's an OH alcohol, basically. Very, very easy. Nice. So it's a OH bond. So we know it has to be an alcohol. So O to H bond. Done. So put this out of here. Alright, let's do the next part. B. The mass spectrum of chemical P is shown below. The molecular ion has a very small peak at 88. So 88, where is that? There we go. So that's 88. So that's our molecular ion. So that's our molar mass of our molecule P. Write the molecular formula of chemical P. Easy. So the best way to do this is, okay, we know that there's one oxygen. Get rid of that oxygen. So if we know the total is 88, minus 16, get that oxygen molar mass out. So 88 minus 16, we get left with 72. This is what I tell my students to use. Use this formula. CN2N. Start guessing. Start guessing values that fit this. If they get close with this. For example, let's say N is 4. So 4, 2, and so, it's supposed to be hydrogen. Hydrogen 2N. So it'll be basically hydrogen. So 8. Let's see if this molar mass is close to this. So 4 times 12 plus 8. 56, it's very far. So what about if I put a 5 here now? So I put a 5 here. It means this has to be a 10. Let's see if I get close now. Times 5 plus 10. It's 70, so it's very close. So the only difference is it means that it has to have, this has to be 12. So the hydrogens have to be 12 basically. And that is it. Done. So now that actually gives me 72. So put that oxygen back. This is our molecular formula. I just want to double check it again. So 4 times 12 plus 12 plus 16. Yes, 88. Beautiful. That is our molecular formula. So C5H12. So C5H12 oxygen. Done. Nice and easy. Let's go to the next part. I tend to identify the MZ ratio of the base peak. So remember, your base peak is the one that's the most abundant, and it's always relative intensity is 100. So where is it? The question is, it's this here, which is what? Well, it's really hard to. There it's there. So that's 1, 2, 3, 4, 5, 6, 7. So it's 57. So 57. State the formula of the fragment that is removed from the molecular ion to form the base peak ion. So be careful. It's the fragment that is removed. So it's going to be an radical. So think about it. If we have a molecular ion peak, remember it's a positive charge. So this is your molecular. Remember the formula, molecular ion peak? And it's positively charged already. When it breaks down, when it forms to other fragments, we get an actual base peak. So this, let's say this is our base peak, so base, and it's positive. And we're going to release a radical where it doesn't have a, where one of its electron is not bonded. Unbonded electron, it has an unbonded electron. So we have a radical. So this is your fragment, and it has, we normally, with radicals, we put it like a dot. We do a very dark dot. And so, yeah, we normally put it as a very dark dot for a radical. So that is what we want, this radical here. How do we do that? Quite easy. Because if we know the molecular ion peak is 88, that's the molar mass, and I know the base peak we just calculated was 57, what's 88 minus 57? This tells me that this fragment has to be, the molar mass has to be a 31. And let's just guess. So I know normally fragments are like CHO in this case. Is it? Yep, because it has oxygen. Now, is that 31? Let's check. 12 plus 16 plus 1. 29, so close, just 2 more. So it has to have, the hydrogen has to have 3. Like that. Let's check. And it has to have oxygen, of course. Let's check if that makes sense. So 12 plus 3 plus 16. Beautiful. It is 31, and make sure you put a dot, because that's showing it's not a fragment, but no, it is a fragment, but it's not, doesn't have a positive charge. It is an actual radical. So CH3, oxygen, and put a dot there. Nice, easy radical. Beautiful. I haven't seen these questions. They're very rare. Wow. But yeah, it makes sense why it should be. Yeah, damn. It's in textbooks, but it's used as examples, but I've never actually seen it in a question. So this is quite new. Not too bad. Next question. The H proton NMR of chemical P is shown below. Beautiful. So we can see that it has 3 hydrogen environments. Identify one feature of the proton nucleus that enables peaks to be produced in the H NMR spectrum. Easy. So why do we have proton NMR and carbon NMR? What is really unique about this? This is why. Basically, they have, we know a nucleus. The nucleus of an atom. So the nucleus is basically positively charged because it basically contains neutrons and protons. So it's overall a positive charge. Now, so think of it. It already has a positive charge. It also has an angular momentum that rotates it around its axis. So imagine, so it has a positive charge and it also has an angular momentum. These two basically combine and both give it its, it makes it like a magnet, a little small magnet. And remember, these magnets, it's not for all of them. By the way, it's not, this magnet, not all atoms basically create magnets. There have to be a certain condition. And this condition is that the number, your overall atomic mass must be an odd integer. What do we mean? It cannot be an even. For example, if it is an even, what's going to happen is you basically will have the same number of protons and the same number of neutrons, and they will pair, and hence they will just cancel out. They won't actually create an uneven magnetic field where you can basically find it. And that's why basically, if you look at so for our conditions to be met, they must be odd, and that's why you have H1 NMR. Number 1 is your atomic number, and it's odd. And also carbon 13, that's also odd. These are why they're mostly used for these, spectroscopy. So yeah, now in this question, I don't think you need to go in detail. It's only 1 mark. So just basically like, by the way, we call this spinning, this angular momentum that causes it, we call it a nuclear spin, because the nucleus is actually spinning. So, and so that is what allows it. It's that positive charge and that nuclear spin that allows it to actually behave as a magnet. And so because it behaves as a magnet, we can actually control it. Like when we push it in a magnetic field, it will rotate towards that magnetic field. And hence we can basically measure molecules with it. So I think just the most basic. So we'll just say nucleus. So identify for one feature. I mean, you can identify so much. You can say odd. It has to have an odd atomic mass. It has to have like nuclear spin. Yeah, or act as a small biomagnet. Yeah, I'm just gonna say basically nuclear spin in this case. So it has a nuclear spin that basically allows it to behave as a magnet. Beautiful. The carbon NMR of a chemical P has 3 single peaks, so also has 3 carbon environments. Draw the structural formula for chemical P. Beautiful. Now, we learned that it was 88. Look at this. We know this straight away tells us that it's an alcohol. It cannot be a ketone and an aldehyde. Think about it. Because if we have two, look at the molecular formula for this. If you have C, and it has to have an OH, how many hydrogens are we going to form? So we have 1 here, 3, 5, 7, 9, 12. That is perfect, 12. But if we had it as a ketone, look at the big problem. Or an aldehyde, it's not actually going to form properly. So CC, and let's say we had a ketone here. C. We have these hydrogens everywhere. Okay, we have 3, which is 5, 7, 10. We'll form 10 hydrogens. But we have overall 12. Why? If it was a ketone, it has to have 10, which is wrong. So, and also it's the same for aldehyde. So if you think about aldehyde too, you have CC, let's say an aldehyde, you have oxygen H here, C, and a C. Also, this will form 3, 5, 6, 7, 8, 9, 10. So also hydrogens are 10, which we overall have 12. So it doesn't also make sense. So it only forms an actual, that really basically tells us it is an alcohol. But what alcohol structure will give us 3 proton environments and also 3 carbon environments? Let's do it. So it cannot be a straight carbon. It cannot straight because then you will have 5 carbon environments. So it has to have symmetry. So can we have CC? What about if we have a C here and a C here? Now we have symmetry here and a C and an OH here. Does that give us 3? So let's think about that. Does that give us symmetry? Because we have symmetry. Let's think about it. So if we have all these, let's see if that gives us symmetry. So we have, in terms of, we have to have 3 carbon environments. We have 1 here. It's not symmetrical, this one here. These carbons here are both symmetrical around this carbon, so we consider them as 1. And also this one here. So that's 3 carbon environments. That's great. What about the hydrogen environments? We have 1 here. Again, because of symmetry, we consider those 3 as 1. And also this one here. So that's 3 hydrogen environments too. So that is actually perfect. This is our structure. So this is great. This is our structure right here. So we want to draw its structural formula now. That was nice. Yeah, this was a great question. So hydrogen. Basically just put hydrogens. Normally they take very long, but yeah, this made sense. There had to be symmetry for 3 carbons and 3 protons. Done. Yeah, looks nice. Explain with reference to the structure of chemical P, why there's a singlet around that 0.9 parts per minute. Let's do that. So we know it's a singlet. Yep, so that's the H. Yep, so there's a singlet here. Why is that? Well, let's use the n+1 rule to tell us why it is. So if we use the n+1 rule, it's a singlet, so it equals 1. N is equal to 0. What does that mean? It means that the adjacent carbon, the adjacent carbon basically has 0 protons. Now, is there a carbon here that actually has 0 protons? Yes, it does. Sorry, where is it? Where's my highlighter? This one. This carbon has actually no, hydrogens. It actually has no hydrogens. So, protons basically. And so that makes sense. So we can say, to get 1 mark basically, using N1+ rule, the singlet means that the adjacent carbon has no hydrogen. But which one of these other carbons or hydrogens told us this? Which? Could it be these 3 here because of the symmetry, or could it be this one over here? Now, to know which one, we have to look at it in terms of, we have to look at it in our data book, basically. So it's 0.9, was it? Parts per minute, per million. So 0.9 for a proton amount. Yes, so 0.9. Yep, only this one's a 0.9 here. So it has to be an RCH3 group. And which one has an RCH3 group? It's only these ones. Oh, what? So it's only these ones. So these ones actually created that peak. That adjacent to it, this carbon here had no hydrogen. So that explains it. So it's a RCH3. So let's write that down here. I don't want to forget it. CH3. So let's write something down. So we're going to talk about basically the n+1 rule and simplify all this for 2 marks. All right, let's use a different color. So let's say using n+1 rule, the singlet means that the adjacent carbon has no hydrogens. Beautiful. And so this is a different color. This peak is produced, why? So this peak was produced by these ones over here, the RCH3. So this peak was produced, by the RCH3 groups that is adjacent. So that is adjacent to the carbon, that has no hydrogens. Beautiful. Not too bad. I actually really enjoyed this. I typically don't like these kind of questions. But this one looked more nicer. So, question 9. Let's have a smash at this. Anhydrous cobalt, anhydrous cobalt 2 chloride is a light blue solid that hydrates in the presence of water. When this hydrates, water molecules attach to it. Dissolving that COCl2 in water will create an aqueous equilibrium, the system shown below. So yes, they actually simplified it for us. So, all right, we've got these. The hydrated COH2 aqueous, so this one here, is pink, so it creates pink, and COCl2 aqueous is blue, so this one is blue. This equilibrium system is useful when investigating the equilibrium because of the different colored ions. All right. A teacher demonstrates the cobalt-2 chloride aqueous equilibrium system to their class using a fume cupboard. So, okay, they're using a fume cupboard. Cobalt-2 chloride solution has several hazards associated with it. State the reference material that the teacher should read when planning their demonstration to ensure that the cobalt chloride solution is handled safely. This is one of the most easiest questions. Remember, whenever you do an experiment, your teacher will basically give you like a safety data sheet or read it out to you, and basically just tells you if it's like, flammable, if that, for example, this cobalt chloride, if it's flammable, if it's like it creates irritation in your eyes. She's just going to read out their safety materials. She has to, because it is kind of the very important thing to do. Yeah, so the reference material that they basically read out is your safety data sheet. That's what she has to do. So, let's use the color of this. Safety data sheet. Easy. The following table details the experimental procedure followed by the teacher and the observations made by a student. All right, let's have a look at this. So experimental procedure step 1. Use a beaker to dissolve 2.6 grams of the anhydrous COCl2 crystals in 100 milliliters of distilled water. Okay, so right now they're basically just, distilling of water. And so what did the students observe? COCl2 crystals are light blue. When the crystals are dissolved in water, a light pink solution is formed. So basically, when they dissolved this solution here, which was blue initially with water, it basically went back to the backwards reaction was favored, and hence it gave us a pink color. That's what they just told us. All right. Put 5 milliliters of a solution into a test tube. All right. Light pink solution is in the test tube. Makes sense because, right now it's light pink. Step 3. Add 6 moles of hydrochloric acid solution, HCl dropwise to the test. And what that do? As more HCl is added, the pink color of the solution changes to purple and then to blue. So basically it had to go to the right. Which makes sense because we have the Cl minus, these chlorine ions. HCl is basically, when you're adding HCl, you're increasing the concentration of these HN ions. And remember, the Chapman's principle, the system's like, oh my God, someone's put so much chlorine into me, I need to find a way to get rid of it. The way we'll get rid of it is going through the right. It's going to go to the right reaction because it will form these products, and these are going to basically be, used up. And that's why it's going to reduce that chlorine, and that's what it will bring it back to equilibrium. So if it's going to the right, we can see that, yes, blue should be formed. But I'm quite confused. Why did they say purple too? Solution change to purple and then blue. So if it changed to purple, normally red and blue. So if you have red and blue, that makes purple. But could pink. Yeah, could pink and blue. So sorry. Pink and blue, could have made purple. So that makes sense. 4. Place the test tube from step 3 into a beaker of ice water. Okay, so if they're putting ice water, all right, they've decreased the temperature. The blue color of the solution changes back to pink. So basically the backwards reaction is favored when you put it in when you decrease the temperature. Beautiful. And that could actually tell us a lot. It could tell us about the enthalpy change. Is it positive? Is it exothermic, endothermic? And let's just read the questions first. State the dependent variable in the experimental procedure. Whoa, what are we actually measuring? The student demonstrates the cobalt chloride aqueous equilibrium to their class using a fume cupboard. Now, yeah, it's not that easily to, like, I don't actually understand what it is. What are they trying to measure? I mean, they're observing, most of them are absolutely just observing color change. You can see here, all of these, like pink, you know, they're all observing color change. You can see blue, pink. I think they're looking at the color change, and that's what's telling us what's happening. So their dependent variable, what they're measuring is basically the color change. I think that's your dependent variable in this question. Because, yeah, they're not actually, they didn't tell us anything about, like, you know, what they were measuring. But, yeah, they look like they're measuring color change, like a qualitative analysis. They're just looking at, and, yeah, that's what they're measuring. So, color change. Consider steps 1 to 3 of the experimental procedure. What is the independent variable in this first part of the experimental procedure? So what's the first independent variable? Remember, your independent variable is what you do, what you change to make, to measure, like, that has an effect on the dependent variable. So, for example, use a beaker that dissolves 2.6 grams of anhydrous COCl2 crystals in 100 milliliters of distilled water. Really, it doesn't do it. Yeah, that's normal. Put 5 milliliters of solution to test tube. Okay. Add 6 moles of hydrochloric acid solution to dropwise. This here looks like our actual independent variable here, because that's when they basically did a change. They changed it. They put hydrochloric acid concentration. So basically, they've increased that chlorine concentration by adding the hydrochloric acid, and they measured the color change. So, and it had an effect on the dependent variable. So yeah, that could be one of them. So the concentration of hydrochloric acid could be an independent variable, because it's saying what is the independent variable in the first part of the experimental procedure from 1 to 3. That looks good. So only from these, the hydrochloric concentration. So concentration of HCl. Done. Hope that's right. Use Le Chatelier's principle to explain the student's observations in step 3 of the experimental procedure. What was step 3 again? Add 6 moles of hydrochloric acid solution to HCl, dropwise to VCE. We just explained this, remember? They added HCl, which basically increased the concentration of that chlorine ions. And so, basically, the system was at equilibrium. Now, equilibrium is disturbed. Easy. So, now what Le Chatelier's principle states is that the system is going to try to counteract that change. It wants to, because of this has increased, it's going to shift to the side, so of course it's going to shift to the right to counteract that increase in concentration of chlorine gas, and hence results of course in the blue color. So the equilibrium position shifts to the right to counteract that increase in chlorine gas. And yeah, like, it's one of the most easy questions. We just explained it. How much marks was it? 3 marks. So easy. You just see what we happened. So we're adding hydrochloric acid, increased concentration of reactants. That's 1 mark. Explain what Le Chatelier's principle does. That's 2 marks. And what the equilibrium, where would it shift? And what happens to the color change? That's basically it. Let's write that down. Use green. So that was the addition. So the addition of HCl increases the chlorine ions in the reactants, we said. Beautiful. Let me put it by Le Chatelier's, I'm not spell it, principle. This will disrupt equilibrium, resulting in a change in the position of equilibrium The equilibrium shifted where to the right. So the equilibrium shifts to the right, to partially counteract. So partially to counteract the increase in concentration of chlorine. So what's the Cl minus. This result, it went to the right, and what was it? Blue color. This results in the blue color. And that's why there was blue color here on step 3. Then it turned to blue. Beautiful. Nice question. State what is meant by accurate data. Remember, accurate data is when the data is very close to the true value. It's like accurate data is like basically data that is, how close is it to the true value? Sometimes they can say what is meant by precise data. Precise data means that the range of those data, how close are those ranges? Are they very closely related with each other? That means they have a very high precision. So yeah, accurate means how close are the values or the data points to the true value. That's what that is. So accurate data. So accurate data is data. So data that is close to the true value. For easy 1 mark. Just define what is accurate data. Next question. Explain whether the observational data obtained in step 3 of the experimental procedure can be described as accurate. So step 3. Is it accurate? Add 6 moles of hydrochloric acid solution, drop ice to a test tube. As more HCl is added, the pink color of the solution change to a purple and then blue. No, like if you think about it, this whole procedure is useless because it's like we're using actually qualitative analysis. So it's people's eyes that are looking. We're measuring through our eyes, which is not something that you can measure in terms of accuracy. Because look, normally when we do accuracy and stuff, it's basically, we measure it numerically, like in numbers, or we call it a qualitative analysis. And that's what we can do. If we have it in terms of qualitative analysis, then we can compare it to the actual true value, and hence we can determine if it's accurate or not. But if it's a qualitative analysis, we're just observing a color change, which for some people, they say one's colorblind. How is he going to look at it? So it's not one of the best tests. It's not very accurate. First, it's not very accurate, but it is a qualitative analysis, and we can't even compare the observed value to to any accurate value. So yeah, it's very not accurate. So 2 marks. So let's write what we said. So we're going to say the procedure is not accurate. It's just this color here. So the procedure is not accurate as observing a color change. So observing a color change is a qualitative analysis, and not quantitative, Sorry for those spelling mistakes. So let's use a different color to explain. Hence, we cannot compare the observed value to an accurate value, as there is no numerical value to compare with. Beautiful, that is it. 2 marks, nice. F. Use the student's observations in step 4 to identify the thermochemical nature of the equilibrium reaction. Justify your answer. This is what we just talked about. Why did they just randomly put it in the iced water? And like what we said, this could be actually, this can help us a lot because we can actually, determine its thermochemical nature. We can determine if the reaction is endothermic or exothermic. Now, it's a 50-50, but we could actually, let's guess first, it is, exothermic. It means that energy is released on the ending side. So, because they basically placed it on a beaker of ice water, they've decreased the energy because they've decreased the temperature. If you decrease the temperature, you decrease the energy. So the system's like, oh no, someone's decreased my energy. I need to find a way to increase it. So the way it's going to increase it, it's going to go for the forward reaction and hence should form a more blue color. And does it do that? Did they observe that? Nope, they observed the pink color. So it's actually not exothermic. It has to be the other way around and endothermic. So we can show it. We just determined it. So it's endothermic. And we just need to explain what we just did. That should be the easy marks there. Very nice, enjoyable question this was, guys. So the reaction is endothermic. So the reaction is endothermic, and we can say when the temperature was decreased, the equilibrium position, where did it go, right or left? So what happens was energy was it was, what's happening with, oh my god, so the reaction when the temperature of the system was decreased, so we're saying it's actually endothermic. So endothermic means energy is on the right. So decrease, yep, it would go to the left if it was endothermic. Yep. So the reaction when the temperature was decreased, the equilibrium went to the left, and hence the increase in pink color, means the forward reaction is favored. The forward endothermic reaction is favored. Endothermic reaction is favored. Beautiful. Beautifully and done. So last question 10. How much is it? There's only 2 parts and they are very long questions. Hopefully it's a good topic we can talk about. So, from a chemical point of view, proteins are by far the most structurally complex and functionally sophisticated molecules known. This is perhaps not surprising. Once realizes that the structure and chemistry of each protein has been developed and fine-tuned over billions of years of evolutionary history. And damn, they actually took it from molecular biology of the cell, this book here. If you do a biomedicine degree at the University of Melbourne, you will actually use this book to, I believe, in second year. And it was actually a nice book we learnt from. Yeah, damn, they actually used a quote from it. Okay, so let's look at the question. Describe how the structure and the bonding of each protein makes its shape unique. So we want to talk about structure. So remember, structure in terms of proteins. We have 4 structures. We have the primary, secondary, tertiary, and quaternary we can talk about. And we need to talk about the bonding that is evolved within them. And why it creates its unique shape. And it's 4 marks. And you can actually draw very much like diagrams. Make it very nice. I think it really shows your intellect in a way. So, okay, first, what we're going to talk about is the primary structure of a protein. And what it is, it's basically the amino acid sequence. So, it's like, let me kind of think about, so the primary structure is basically, no, not this, so it's basically, it's like the amino acid sequence. So if I just basically duplicate these, imagine these are all amino acids. Nice amino acids here. These are amino acids. Right over here. All these are amino acids. And so basically, it's like a sequence. You can see that they're linked. They'll be linked by an actual, there's only, in primary structure, there's only one bonding, and that's called peptide bonding, which is a covalent bonding. That's between amino acids. This is peptide bonding, and that is it. So basically, it's very important. Your primary structure is the beginning of a protein. It's basically a very unique sequence because it has a different all amino acids. That's why it's basically very structurally complex. Because imagine it's like a code. You have all these different, imagine alphabets. Of course, we have, only little alphabets, but when you mix them around, make words, you make billions of words. Like it's thinking that like that. These are amino acids, the building blocks. And so, yeah, they are all linked by polypeptide long bonds, which are your bonding we talked about. And yeah, what this gives it is basically its chemical properties. Because remember, all those amino acid sites have, R groups. They have R groups. Some R groups are polar, some are non-polar. And, those, amino acid groups, side groups, is what influences it to fold. So, overall, primary structure is not, it's not folded right now, but the primary structure is the actual, just the amino acid sequence that is linked by polypeptide, bonds. And so let's write that down. So I think that should give you 1 mark in terms of how to explain that. So, all right. So we want to just not write, I'm going to write a lot, so I want to try to be very detailed and nice with this. So, the primary structure, we said, so the primary structure of a protein, so it said that it's unique sequence of amino acids, so sequence of amino acid, basically which are linked by polypeptide linkages. Which are all linked by polypeptide linkages. We know that the primary structure gives proteins its chemical, we said its chemical properties. So chemical properties due to the amino acid groups, so side groups. And they also influence those, those side groups, they influence the folding of a protein. They influence the folding. Done. That is what a primary structure is. It is the beginning of a protein. Here it is. A nice, easy primary structure for you. Nicely drawn. The other ones are going to be more complex, of course, but it does give like a nice... let me just put that there. Let me just kind of make it a little smaller. Right there. Let's put it there. That's what it will look like. Now we're going to talk about the secondary structure. Now, basically the secondary structure is where that primary structure now folds. Now, it folds and gives rise to 2 main structures, and that is the alpha helix and the beta sheeted. So let's have a sketch of those alpha. Of course, I don't know how to, it's really hard to draw an alpha helix, so I'm just going to draw like just a rubbish one. So it's like this. So remember, secondary structure is only 1 polypeptide sequence. So you can see it's still 1. Yeah, something like this. Let me draw it nicer like this. Okay, so we have something like this. Like it's in terms of 3-dimensional shape, it'll look like this, and it's all basically bonded. Oh my god, it's actually bad. Okay, so can you see how it's like this is called alpha helix. So alpha helix. And basically what gives rise to the alpha helix, and we'll talk about the beta sheeted ones, both of them are basically stabilized by the hydrogen bonds between the backbone of the amide, the amide hydrogens and the carbonyl oxygens of the polypeptide chain. The basic polypeptide chains? Those are the amide hydrogens and the carbonyl oxygens were basically... They go through, of course, hydrogen bonding, and that's what basically stabilizes these shapes, the alpha helix and the beta sheeted. So the beta sheeted will look like, it's like this parallel. It's like this kind of sheet of parallelity. I don't know, something like that. It's like a sheet, and then here you got your atoms in it. It's like a sheet. And so that's your beta sheeted. Not the most nicest, but yeah, that does the work. So yeah. And so, absolutely. So overall, it's when basically so when we're talking about the structure, it's basically when the primary structure folds and creates those secondary structures, and we know that there is 2 of them. There's alpha helix and beta sheeted. That is structure. And what are the bonding? They are hydrogen bonding. It's what creates them is the hydrogen bonding between the amide hydrogens and the carbonyl, oxygen atoms. And yeah, beautiful. So they will be like this basically. They'll like form these bonds. So it creates this nice structure. Beautiful, those bonds. So let's write that down. So secondary structure are the folding. So are the folding of the primary structure. The primary structure, which gives rise to 2 of them. So gives a rise to two main structures. So oops, two main structures. The alpha helix and beta sheeted. So B sheeted. So beta sheeted. And these patterns, so these patterns are produced, these patterns are stabilized by hydrogen bond between, so between the amide hydrogen, so the amide hydrogen, so and carbonyl oxygen, or atoms of the polypeptide sequence, polypeptide sequence. And that is beautiful. That is a nice, of course, okay, luckily there's still more places for the other three. Yeah, and those are what they are. So I'm just going to make these smaller, put them right there. Oops. Why is it not taking these? Let's make these smaller. Right there. That here. And put it right there. Now let's talk about the tertiary. Now, so basically the tertiary structure is the overall three-dimensional shape of a single molecule. So for example, you know how we had a primary structure, which basically was just like a straight, sequence of amino acids. And so basically when they folded, it created two structures, which are the alpha and beta sheeted, and that's created the second structure. Your tertiary structure is basically when it's still one, of course, polypeptide chain, but it's like the overall three-dimensional shape of a single protein molecule. So it looks like a very it looks like this basically. It's like a mix of beta sheeted, alpha helixes. I really don't know how to draw it, but it looks like a bunch of mess. It's like a sequence. It's only one sequence, but it has, let's say, alpha helixes, beta sheeted, alpha helixes, beta sheeted, just a mix of everything. It's like a protein. It's a big it's a bunch. It's only one sequence. You can see it's only one sequence. It's not two. So that's what a tertiary structure. It's only one single protein molecule. And basically this is stabilized by the R groups between those amino acids. And there's actually a lot of bonds that occur. That includes hydrogen bonding, ionic bonding, disulfide bridges, dispersion forces. All these forces are basically what stabilize this molecule, the tertiary structure. So yeah. So when we talk about the structure, that's what it is. It's a three-dimensional shape. Yeah, and the bonding are basically a mix of hydrogen, ionic, disulfide, and dispersion. I forgot there's some more if you do uni. It's like van der Waals forces and other stuff, but that's no need for that right now. So yeah, that's what they are. So I'm just gonna write that because I really can't think of something else. I'm trying to think of other stuff, but I'm trying to be like answering the question, but I think I'm just, yeah. Come on. Come on. Why? There it is. Let's do this. Nice. There it is. That is your... Yep. So I'm going to use a different color now. I'm going to use this yellow. So the tertiary structure. The tertiary structure is the overall... And remember that... So if you think about it, the tertiary structure is basically what creates the active site of an enzyme. It's a three-dimensional shape. So it's the overall 3-dimensional, I think, not 3D, dimensional. So you want to say three-dimensional shape of a protein. It is stabilized. It is stabilized by bonds. By bonds between R groups and between R groups. So R groups of amino acids, of those amino acids, So, and what so they include, we said they include hydrogen bonding, hydrogen bonds. So hydrogen bonding, ionic bondings, ionic bonds, dispersion forces, disulfide bonds, disulfide bonds, etc. Like etc. And yeah, that's what really gives that. What about the quaternary structure? The quaternary structure is now, it's basically, you know how we said that overall the tertiary structure is basically made out of one sequence of amino, like a, you know, a protein, like a, what do you call it? Like a sequence of amino acids. Think of the quaternary structure a bunch. So basically, let me think. Tertiary structure is like this here. It's like this here, which is just basically one sequence of an amino acid. And we call it one subunit. Imagine having like 4 more different ones. For example, I'm just going to basically copy this and try to use another example. So if I just copy this here, copy, come here. So let's just try to give an example. So like, for example, let's say you have this here. And basically you have another subunit. So that's another polypeptide chain. And so, you know, it goes blah, blah, blah. Has, you know, has nice parallelity, alpha helixes, blah, 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 parallelity, alpha helixes. It looks something like this. You can see totally different structure, but there's 2. If there are more than 2 subunits, if there are more than one subunit, this creates a quaternary structure now. And normally one of the most, so overall, the quaternary structure is basically like composed of more than one polypeptide chain. And so, yeah. And by the way, the bonds are the same as the tertiary structure, by the way. It's those disulfide bonds and all the other stuff. So, one of, because, that's all I know. Like, do we say anything else? Because it's not a lot. Like, one of the most example of quaternary structures, one of the most is hemoglobin. Hemoglobin, which is a protein that is used to basically, you know, in your cells for oxygen. To carry oxygen. So yeah, normally hemoglobin has 4 subunits. These are 2, so you would have like another polypeptide chain. So like, parallel, you know, alpha helixes and stuff. It looks like that. And then of course you got let's say another one, which basically parallel alpha helixes, and looks like that. There it is, like 4 subunits like this, and that's what basically creates that quaternary. So more than one polypeptide chain creates this quaternary structure, which looks like that. Let's write that down. Well, I don't know what to write. It's like not a lot I can write about it. Let's use a different color. Let's use this red. Actually, use red. Let's use red. So quaternary structure. Quaternary structure is composed of, so the quaternary structure is composed of more than one polypeptide chain. And so the bonds are the same. So the bonds formed between those polypeptide chains are the same as the tertiary structure ones. So I'm not going to write them again. So formed between polypeptide are the same as the tertiary structure. And I mean, I'm not gonna write an example of hemoglobin. I think that should be enough. I think it gives enough detail. Yeah, perfect for 4 marks. Wow. Now let's talk about B. Last question. Okay. Discuss using the lock and key model how the structure and bonding of enzymes allows them to catalyze only specific reaction referred to the optical isomers and chirality in your response. Easy. So it's only 3 marks. So I think 1 mark comes from basically this, like, defining what the lock and key model is, and basically we'll then talk about how the structure and the bonding of the enzyme allows them to catalyze only specific reactions. And how, like, for example, we could talk about the active site of an enzyme is like very unique, and we know, and it talks about referring optical isomers, and we can also talk about let's think. So okay, let's first go one by one because there's a lot to talk about here. All right, so Using the lock and key model. First, let's talk about the lock and key model. What the lock and key model refers to is that the enzyme is, think of it as a key. So, think of an enzyme, a nice enzyme like this, as like a nice key, like that, like a Pac-Man. It's like an enzyme, and basically, of course, this is your active site. Think of this as your basically lock. And this is where your key thing goes in there. So this is your active site. Beautiful. And say then you have your key, which we call our substrate. This is your key. That's what the lock and key method is. Basically, what it just refers to that is that your lock is very specific to that key or that substrate. And so it overall like models how enzymes have this high specificity of its substrates. It doesn't allow other substrates to bind. It only allows it's one substrate to bind in, and that's what it means basically. So that's what we probably talk like. We'll just say something like the lock and key model refers to how the active site of an enzyme, which is the lock, is a perfect fit for the substrate and hence highlights the specificity. I mean, that should be enough, yeah, to get that first mark. So let's write that down. All right, the lock and key model refers basically, what was it? That the active, so it refers to that the active site, so it refers to the active site of an enzyme, which is basically the lock, is a perfect fit for a specific substrate. So substrate, which is your key. That's what the lock and key is. Basically, this model highlights the specificity, highlights the highlights the high specificity of enzymes for their substrates. Beautiful. So I think that basically like you should get you 1 mark talking about the lock and key model. And so it referred to optical isomers and chirality in your response. Now, I think the first thing that comes to my mind is talking about how, all right, so we know that the active site, I think we'll talk about the active site and how very important it is to have this shape. So the active site is very unique. We know that the active site is very unique. And it's 3-dimensional. That's what we said. Remember, it's a tertiary structure. It's a 3-dimensional pocket. And it only allows the correct complementary shape, not other ones. It only allows the correct complementary shape. So, for example, say we have like a nice here. And say this is your active site. Let's say this is your active site. Before we even talk about it, we need to talk about chirality first. So basically, what do we know about chirality? We know that many of the amino acids are basically, they have a chiral carbon, or more than one, let's say, more than one chiral carbons. And remember, if they have a chiral carbon, they exist as 2 mirror images form. So they exist as 2 mirror images in terms of form. And these are what we call optical isomers. And we know that, remember, optical isomers are what? They have the same sequences of the bonded atoms, but different arrangement in the 3-dimensional shape. For example, let's talk about one. So let's make an example here. Why it's important to know what how basically your enzymes are very, very skilled in determining which one is the correct optical isomer to take in. So let me just put that there like that. All right. So let's say this is your active site. And let's say you have a nice diamond here. You have a circle, a triangle, and a square. And let's say this is your substrate. This is your active, and this is your substrate, which has this square on top. Bottom is the diamond. On this side is your triangle, and this is the circle. So basically, if you put this this substrate into the active site, it would fit perfectly. It's complementary. But when it's an enantiomer, so when basically there's two forms of it, because you can see that it is chiral, this carbon is chiral because it has all different side groups. So if I draw a mirror image of this, so basically like this, like that. Sorry, not what am I doing? So if you draw the mirror image, the triangle would be here now, the circle would be here, and the triangle would be here. Let's keep this, just duplicate that here. Now, if you actually put this in here, it won't fit. You can see that it won't fit here, and the circle won't fit here. As many times as you want to rotate it, you can rotate it 100, as many times as you want it, it will not fit complementary anymore. So, it's something that's what's something that's cool about, let's call this, molecule A, of course, let's call this A and B. What's something cool about enzymes is they can actually determine which is the correct substrate to fit in. It has this high, professionalism that it can actually take, even though the structures of these two in that optical isomers are very, very closely related, it knows which one's not going to fit. It knows which one's wrong. And so that is why enzymes are very basically, they have this high specificity. And so, yeah, we can talk about that. I think when it's talking about the optical isomers and the chirality in your response, it says. So we talked about the lock and key. We need 2 more marks. So, we can talk about basically like, I think the most easiest one is we'll talk about like, we talked the chirality. So we need to talk about chirality and how it's crucial for enzyme specificity, like we said. And we know basically most of the amino acids are chiral. Like when we see them, they have carbons where they basically have 4 different times of group, and so hence we have optical isomers, and so so that's what we'll probably talk about. So let's talk about that. So we're gonna say chirality plays an important role in enzyme specificity. Many biological molecules, including amino acids, of course, including those amino acids, are chiral, meaning that they exist in 2 mirror image forms called optical isomers, and we know that optical isomers have the same sequence, so have the same sequence of atoms, but different. So they have the same sequence, but they have different 3-dimensional. So three-dimensional space. The spaces are totally different. As we said here, they won't fit perfectly. See, even if that makes sense. Beautiful. I think that kind of talks about chirality, and I think we'll just make an example like this. We'll just explain an example. For example, molecule A, and I think you can actually put an actual diagram. You can actually draw diagrams if you want in an exam. This is actually good. The examiner sees that you are, supporting your learning by actually writing these things. So you can see that. Let's just draw these nicely. So here, this one fits. This one fits perfect. This one here, sorry, what am I doing? Does not fit. And we can just make the example. Let's talk about this example. So what I'm going to say, let's just say for molecule A, so that molecule, so, okay. For molecule A, it fits perfectly. It fits perfectly to the enzymes, active site. But an optical isomer of A, known as B, we'll call it, known as B, exists. It will not be able to fit because so it will be not able to fit because the enzymes active site is specific to the three-dimensional arrangement of atoms. So these of atoms are in molecule A. I have no idea if this is going to get the full marks, but I think it goes really nice and detailed. So yeah, how beautiful chirality, we gave an example. I think giving an example of this will give you a mark. And yeah, I hope that makes sense. I hope you guys enjoyed this video. Please make sure to like and subscribe for more future videos like this. I hope if this video finds you well and helps you with your chemistry studies. Have a great day, guys, and take care of yourselves. Bye-bye.